Our speaker for this evening is a research meteorologist with Met. He's involved in weather and climate research and is active in, he's an active science communicator. He's a founder of Big Skies Media. So, ladies and gentlemen, could you please welcome Dr. Noel Fitzpatrick? Noel.
Thank you very much. It's lovely to be here, and thanks to Engineers Ireland for having me this evening. And it's great to see people coming out to listen to some science on a Monday evening. You could be at home sitting on the couch, so thanks for coming out. So we'll have a bit of a sort of a whirlwind tour of meteorology and weather and climate, and obviously we'll have kind of an engineering focus a little bit as well, considering where we are today and this evening. I'll just give a bit of a background as to who I am and why I'm here. And then we'll dig into just how we go about predicting the weather. And then we'll have a little bit of a focus on some big projects that are coming up in Europe that will help improve weather forecasts and improve our understanding of our climate. And then another aspect of our weather, of course, is when it turns a little bit extreme. So we'll look at that, how we're trying to understand it better, how extreme weather occurs, and some examples of that we've had recently. And then we'll finish on what Ireland's future climate may look like. So just a little on my background. So I am a research meteorologist, and at the moment I work for Met. My main focus is in satellite meteorology. So essentially what that means is using satellites to observe and monitor our weather and to better understand our climate. I also represent Ireland on a number of European bodies related to satellite meteorology and climate. So my background academically is in climate and glacier research. So essentially looking at how our planet's snow and ice is changing as our climate warms. So I spent a number of years in Canada and in other places, other cold places, generally at the Arctic and in Alaska. And that is to study these effects. So generally you would travel more often than not. Let me see where that's popping up there. Okay. More often than not, you're traveling to these very remote locations, usually by helicopter or by plane. And then you're getting dropped off and you have to travel around often by skis. Sometimes in the Arctic, you're using snowmobiles. And the conditions are usually fairly testing. You're camping usually out on the snow or on the ice. This picture here, this is me in Svalbard in the Arctic, where I spent a few months, and it's below -40 in that picture. So really, anytime you spend outdoors, you're sort of checking your skin to watch out for things like frostbite and things like that. However, the locations are spectacular. They're beautiful places to spend time and beautiful places to try and protect also. So my main sort of research in that area was building weather stations on glaciers, essentially, and looking at how changing weather patterns were affecting how quickly they were melting. So we would arrive in locations like these. Usually there'd just be a team of maybe 2 or 3 of us. We would carry in a lot of equipment, and then the larger equipment, we would need a helicopter to bring it in. Now, these locations were very remote, so there was no way to kind of bring it in any other means. And then we would go about constructing something that would look a little bit like this. So this is a weather station. It's got lots of different sensors for measuring temperature and pressure and wind speed and a whole bunch of different climate and weather variables. From an engineering point of view, these stations are quite tricky because we're trying to build a stable platform on a surface that we know is going to be changing dramatically during the time that's there, because this is an ice and snow surface. It's going to melt, it's going to change. And also it's a very remote location, and we're trying to keep a very power hungry system powered throughout. So we have to build solar systems and things like that. So one of the other things that I would build when I would install one of these stations is a time-lapse camera to monitor the station and also to monitor the surface of the glacier throughout the period. So this is just a 2-month period, but you can see just how quickly the glacier surface is receding and is dropping down. It's almost like it's been deflated. Now, this was during the summer months, so you would expect to see some melting and some loss. But the gain that's happening during the winter is nowhere near the amount that's been lost during the summer. So year on, year out, there's more and more loss happening. So that was my sort of more my research and academic background. So as mentioned, I currently work for Meteorologist, and I'm also very interested in science communication. I present the Meteorologist podcast, which is a monthly podcast. You can get that on Spotify or Apple Podcasts. And I've also recently launched an initiative called Big Skies Media, the goal being to help people to communicate scientific stories. So if you have a science story or maybe a technical story and you want to communicate it in a language that will appeal to a broader audience, that's something that I'm endeavoring to help people with. So predicting the weather is essentially telling the future. And I think it's amazing that we can even attempt to do that. And this image that we're looking at here is essentially a year's worth of weather as captured by weather satellites looking at the Earth. It's kind of stitched over using imagery from lots of different satellites. And the one thing you can see is just how dynamic and how changeable the weather is. And our atmosphere is considered what's called chaotic. So essentially what that means is that a very, very small change in some parameter or some feature somewhere in the atmosphere can lead to big changes down the line over a period of time. So a way to kind of visualize that is imagine you're standing on the top of a big mountain and you're holding a ball in your hands. And you let go of the ball and the ball takes a small little bounce and another bounce and gradually it's rolling and rolling and it rolls down into a valley and makes its way down to the bottom of the valley floor. And then you do the exact same thing. You take another ball, you drop it the exact same way, but maybe it takes a slightly different bounce, a slightly different wobble, and it ends up rolling and bouncing and ends up a slightly different valley and then continues to roll down. And then your two balls have ended up in totally different locations, even though they started in the exact same location. The reason being is that very, very small changes can have big impacts down the line. And that is what happens with our weather. You could have a very, very small change, very small difference that maybe you didn't spot or didn't properly record, and that can lead to a very inaccurate weather forecast. So therefore, the first step to predicting the weather is having really good observations. So you want to get a really good picture of what our atmosphere looks like before you start trying to predict what it's doing in the future. So we rely on obtaining lots and lots of observations. So we have lots of different systems and networks that we use for gaining observations. So we have traditional things like weather stations, which would be dotted over the surface on the land. We also have ocean buoys, which measure things like temperature and pressure and humidity through the ocean. And then other sort of sensors like radar, for example, that we have at the airports, which tell us about rainfall and other forms of precipitation. However, obviously, these are just sort of point measurements, and you can only have so many of these covering the surface. So you need to look at other ways to gather data. So a great way is our satellites from space, because they can give us a much broader picture of the globe. And then also, we're not just interested in what's happening at the surface. We want to know what's happening through the atmosphere as well. The atmosphere extends, over 100 kilometers above our head, and changes within that atmosphere affect our weather. So we use things like weather balloons, which can take measurements as they travel up through the atmosphere. So all this gives us a picture of what our atmosphere and what our weather is doing in the present before we start trying to generate a weather forecast. So we take all the data and information that we've obtained from our observations, and then we feed these into really powerful computers. So we call them supercomputers or high performance computers. So each of these systems, they're essentially like a whole bunch of very powerful computers all linked together. These computers are some of the most powerful computers in the world. They can take up the entire floor of an office block, essentially. And they are used exclusively for trying to predict the weather. And on these computers, we have what we call weather models. And essentially, weather models are sort of simulations of our atmosphere. They use the math and the physics of what we understand how our atmosphere works to generate a forecast. So we feed all our observations into these models. These observations tell the model kind of its starting point. This is what the weather is like right now at this moment. And we sort of press play on the model to advance that into the future to tell what the forecast is going to be. And then the final step is actually producing the forecast. So this is where your forecasters come into it. They will look at what the weather is actually doing at the moment. So the different sources of observations come from satellite, from radar, from lots of different sources. And they will also then consult the weather models. They'll compare the two. They will know where weather models are strong or where they have weaknesses in different conditions. And they will combine that to generate a forecast. And that could be the forecast that you hear on the news or that you see on your app or on your phone or on the website. So that's how things are done at the moment. And there are some really interesting and exciting projects happening in the next few years that will help us to improve how we carry out weather forecasting. The first is in relation to that weather modeling that I mentioned. So Ireland is involved in a collaboration which is called United Weather Centres. And this is a collaboration on weather modeling. You might hear me use this term, numerical weather prediction, or NWP. If I say that, all I mean is weather modeling. It's sort of maths and physics to predict the weather. So we are in a collaboration with Iceland, Denmark, and the Netherlands. And this collaboration is well underway to develop a weather model that we will all use. And it's due to go live later this year. So what's the purpose of this? Why are we collaborating? So if you think about where we're located, we're interested in predicting the weather for roughly the same location. And in this part of the world, most of the weather is coming off the west, coming from the Atlantic. So it makes sense that we would collaborate, because we can pool all our scientific resources, our computing resources. As I mentioned, there's a lot of computing resources needed to generate forecasts, and financial resources as well to generate a forecast model that we can all use, with the goal of generating a more accurate model that will have better resolution and more timeliness. So what I mean by that is we get more regular updates. We can see how the weather is changing. So we are locating our supercomputer in Iceland. And there are a number of reasons why we've chosen Iceland to position our supercomputer. So the first is actually due to the location that we have access to store the computer. So we want to store it in a very secure location, because weather information is used in so many different aspects of our societies, whether it's for safety, it's for travel, it's for economic activity. So we want to make sure that our weather forecasts are been produced and that they're not disturbed or disrupted. So this is actually a Cold War era bunker located in the Icelandic Weather Institute. It's designed to withstand all sorts of man-made and natural disasters. And it also has multiple power and data links. So you know that it's always going to remain powered. It's always going to be able to get its messages and information out from the computer itself. Another feature that many of you may know is that Iceland has a lot of geothermal energy. And this is a very sustainable form of energy. And we wanted to make sure that our project has a low carbon footprint. So by positioning our computer in Iceland, these supercomputers use a huge amount of power. So it's very beneficial for us to have access to low cost and sustainable energy, and to help us to reduce our carbon footprint. Similarly, as I'm sure you know, Iceland is quite a cool location. And so it means that we can use natural methods for the most part to cool our computer, because these computers, they use a lot of power and they generate a lot of heat, and you need to keep them cool to work at their best. So that will allow us, again, to reduce how much energy we need to use to cool it down, and again, reduce our carbon footprint. Iceland, because it's so good for storing supercomputers, has really good expertise on these kind of machines. As I said, the HPC or supercomputers. So if we have an issue with the machine, there's lots of in-country support that we can rely on. Another major reason why Iceland has been selected, it has excellent data links to the rest of Europe. So there are 3 major undersea cables running between Iceland and the rest of Europe. And these, the most recent of which actually just came to shore around this time last year at Galway. This means that we have secure and robust communications between the centre and between the other collaboration partners. Why is that so important? As I mentioned early on, observations are vital for running a weather model. So we need to be able to get as many observations as possible in close to real time into the machine. So that, what I mean by that is basically there's not much point in trying to generate a forecast if the information is really far out of date, because it's not going to be of any use to anybody, because the weather will have already happened. And that's similar for once you've actually generated your forecast, you want to be able to get it out to the public and get it out to the users as quickly as possible. So good data links are vital for that. So then the supercomputer is built and it's been installed in Iceland. So as I said, it'll be going live in the next few months. Just a couple of numbers to kind of give you a sense of how much activity and how much work this computer is going to be doing. It will be handling in the order of 10 million weather observations every day. So that will be a day in, day out. And that's, again, why those data links are so important. It's a very powerful machine. It's capable of carrying out 4,000 trillion calculations every second. And that has been driven by the weather model. So that's, as I mentioned, is sort of the maths and physics of how the atmosphere works. And that weather model, which would have been written in collaboration, has over 6 million lines of computer code. So a huge amount of work has gone into designing that. The outcome is that we will be getting a weather forecast update every hour, which is a major improvement. So at the moment, we get an update every 3 hours, which in itself is a recent development and a very welcome one. But this will provide us with an increase in frequency by 3. So really, really positive development. So as I mentioned, the benefits of this collaboration, weather forecasts with increased accuracy, they'll be updated more frequently and they have greater resolution. So what I mean by that is we'll be able to see and predict better sort of regionally, locally, how your weather is going to be. That will be very important in particular for extreme weather events, for giving warnings about storms, floodings, things like that, and knowing when and where more precisely these storms may occur. Weather is vital, as you know, for safety, particularly in transport sectors. So aviation, marine sectors will benefit from these improved forecasts. And really any sector that has an outdoor involvement, whether that's engineering or construction, agriculture, even retail, being able to plan ahead, even knowing the forecast, a few more hours in advance will really benefit these sectors. So that is the United Weather Centres. That's one of the big, exciting kind of engineering and science projects that's happening that will help improve the weather. There's another project ongoing at the moment. Europe uses, and all around the world, we use weather satellites, as I've mentioned, for observing our climate and observing our weather. There are different types of weather satellites. Some orbit around the Earth quite close, and they take very detailed measurements, and they pass over different sections of the Earth through the day. And then we have these ones which are further out from the planet, and they focus on one area of the planet and look at it all the time. So these ones here, for example, just looking at Europe all the time. And they're the most useful for weather forecasting, because if your weather is changing quickly, you want to have something looking at it all the time, and you can see how it's changing and get updates regularly. So Europe is in the process of launching a whole new series of weather satellites over the next 10 years. And these will increase greatly the resolution of the imagery that we're getting, and also how frequently we're getting updates from space. So the first of these satellites is actually already launched. It launched about a year ago, and it usually takes about a year to put these satellites into operation, because there's a lot of sort of testing and commissioning that has to go on once they go up. These satellites are decades in planning and building. The level of detail that goes into planning these, and the level of testing that they have to go through before they are launched. So when they're fully operational, there will be 3 satellites working together. The first of these satellites, as I mentioned, which is already in space, is an imaging satellite. And this satellite essentially has a really big, powerful camera on it, and it will take pictures of one side of the Earth every 10 minutes. And that's very useful. That's the imagery that you see maybe if you go on to a weather forecast website, or maybe on the news when you see them showing imagery of cloud as it comes in. That's coming from an imager like this. So this will provide really high resolution imagery, up to 1 kilometer resolution. So that's impressive, because this satellite is more than 36,000 kilometers away from Earth. The other really exciting thing is there's a brand new sensor on this called a lightning imager. We've never had this over Europe before, and it will provide real-time data of lightning storms and thunderstorms as they happen over Europe. So that'll be very useful for our forecasters. The second satellite then, it's a different type of system. Rather than being interested in taking images of the Earth and what's happening at the surface, it's looking at what happens through the atmosphere, so through the whole thickness of the atmosphere above our heads. So it's a profiler, and it will provide temperature and humidity and potentially wind measurements up through the atmosphere. That's very important for running our weather models. As I mentioned, we need as much data as possible, not just at the surface, but also up through the atmosphere as well. And that is also a brand new type of sensor. We've never had that before from space. So that will be a really, really beneficial tool to have when it's launched. And then the final one is a second imaging satellite. So again, it has another camera on it, similar to the first, but it's just focused over Europe, and it will provide imagery every 2.5 minutes. So that will be so useful for looking at rapidly developing storms with resolutions of up to 500 meters. So very, very accurate and very precise imagery. So as I mentioned, the first satellite is up, but it's not yet operational. But I have gotten access to some initial imagery from it. So this is the first image that it sent back of our planet, and that's the view that it has from where it is, 36,000 kilometers away. There's a little video showing of, just to get a sense of the imagery, kind of zooming in to get an idea of how good the imagery is over Europe and over the parts of the world that we'll be interested in. And it will send back one of these images every 10 minutes. So our forecasters, anyone working in the forecasting field, will be able to see updates every 10 minutes using imagery like this. And again, this is test imagery. It's going to improve even more so when it goes operational. You can see some really nice features because the resolution of the camera is so good. So these are the Canary Islands. And if you imagine the airflow is going this direction, and what you can see are you've got these little eddies, these little whirls downstream, essentially, of the islands. This is because the air is flowing and getting disturbed by flowing over these islands, and it generates these lovely features. You can see it in this video. It's incredible. We weren't able to capture this before with the previous sensor because it just didn't have the resolution. This is nighttime, that's why it's gone to black and white, but it'll turn back to color again when the day returns. But you can see these lovely swirls and patterns. Again, just showing the detail that will be detectable with this new sensor. We'll also be able to use it for looking at wildfires. So it might be tricky to see them here on the projector, but there are little fires. This is over Central Africa. These are really small bushfires popping up. And as you know, wildfires are becoming an increasing issue in Europe during the summer months. Imagery from these satellites will be used for helping those fighting fires to know where forest fires or wildfires are at their strongest, where they're moving to, where they're growing, and to help them tackle them. This last product here, so this might look kind of a bit like sort of modern art, but it's actually a thunderstorm. This obviously isn't what a thunderstorm looks like in reality. It's been colored artificially. Essentially, the more red colors are where the cloud is at its coldest. It's kind of opposite to what you might think, and blue is where it's warmest. The significance of that, I'll just play that again, is that it allows forecasters to tell where the storm is at its highest, because the highest parts of a thunderstorm, where it's kind of grown up the most, are where it's most active and potentially most damaging. So by being able to track those features, a forecaster could tell, okay, this is where the most severe weather may be moving towards. They're very useful for tracking severe weather. As I mentioned, there's also a brand new sensor, which is a lightning imager, and this will provide real-time lightning imagery over Europe. This is some storms kicking off over Central Europe during the nighttime. And as I said, this information will come through to forecast offices in pretty much real time, so less than a minute from when the strikes actually occur. This is actually a bit closer to home. So if Ireland is there, the UK, with some storms here over Spain and France, and we see some kicking off as well over the UK. So all these tools combined together will be really, really useful for forecasting the weather, particularly when it comes to rapidly developing storms and severe weather. So severe weather obviously is one of the most impactful aspects of monitoring and understanding our weather. And depending on what parts of the globe you're in, the weather can be very prone to getting some really spectacular and also damaging storms. This was a storm in Oklahoma. I've traveled to the US a few times and I've sort of spotted and tracked some of these storms. More often than not, they occur in a region in the central US nicknamed as Tornado Alley. So essentially it's sort of up through Texas and Oklahoma and Kansas right up through the center. This area has essentially a mixture of different air masses coming together that are really conducive to the formation of big thunderstorms, and these can potentially produce tornadoes also. So what causes a thunderstorm to form? What do you need to get a thunderstorm to form? So there are a number of key ingredients, and this is just sort of a general picture without going too much into the real specifics. The first thing you need is unstable air. And what I mean by unstable essentially is that you have warm air below cold air. That's essentially what unstable air is. And if you just think of it like when you put a pot of water onto a stove, and as the water at the bottom, which is closest to the heating element, starts to heat up, it will start to bubble upwards. And that's because the water is less dense. It wants to rise above the colder air. And the same thing will happen in the atmosphere. If you have warm air below cool air, you'll get that rising air up through the cloud. You also need moisture. Firstly, for the cloud to form, because as I'm sure you know, as air rises up through the atmosphere, it cools, and the water vapor within the air will condense into cloud droplets, and that's where clouds come from. So that you need moisture to form the cloud and also to fuel the thunderstorm, because as water vapor condenses into droplets, it releases lots of heat energy. It's called latent heat. And that is like fuel for a thunderstorm. It keeps it going and it gives its energy. So you can kind of see this in this video. This is approaching a thunderstorm in the US. It's obviously sped up. You can see this kind of billowing that's taking place up through the center of the cloud. And essentially that's rising air is driving up moisture, generating the cloud and eventually leading to a large thunderstorm. So if that moisture and if those cloud droplets and the storm builds high enough up into the atmosphere, it will go into cold areas where the droplets can freeze and form hailstones. And hailstones can grow in size by colliding with other droplets and the water sort of freezing onto them. They build up layers and layers of ice on top of them. That's what forms a hailstone. These hailstones are constantly colliding and bashing off each other within the cloud, and they're generating static electricity. So as I'm sure you know, static electricity, say for example, if you maybe take a jumper out of the dryer or something like that, and depending on the material it is, it might crackle a little bit. And that's because it's been shook around and moved around, and it's generating this kind of static energy. So if you could imagine that process taking place over something as big as a large thunderstorm. So a large thunderstorm can be over 10 kilometers in height, can be several kilometers in diameter. So it's a huge volume. And you've got these collisions and these interactions happening through the space. And it's that energy that gives you the energy for light and gives a thunderstorm its name. So lightning is very impressive on its own. A single lightning bolt can be over 30,000 degrees Celsius. So that's 5 times hotter than the surface of the sun. A single lightning bolt can produce in the order of 5 billion joules. So that's enough energy to power your house for several months from one bolt. And a thunderstorm itself can have up to 1.3 billion volts. So that's about the amount that you would see in a large modern nuclear power plant. So these are enormous amounts of energy in these systems. They're also spectacular. I have an interest in sort of photography and interested in looking at these things. So from a perspective of just forces of nature, they're incredible to witness. You can get some incredible storms at nighttime as well. This lightning here is what's called anvil crawlers. So essentially, instead of bolts that come down to the ground, they travel along the base of a cloud. And the only way I can describe it really is it's almost like looking at like lightning traveling through veins in your arm, or maybe on the veins of a leaf or something like that, rolling over the sky underneath you. Really spectacular. This was also a bolt that was very, very close, that did come down to the ground. And really, really you have to respect these kind of storms, because they're carrying a huge amount of power. So one of the major hazards of thunderstorms we've just talked about is lightning. You can also get a lot of heavy rain and flooding with thunderstorms. And as I mentioned, hailstones can also be a major hazard. Now, here in Ireland, hailstones don't necessarily grow that large, but where you get these large thunderstorms, these upflowing currents of air are strong enough to support hailstones in the cloud for a long period of time. And what that does is it allows these hailstones to grow and accumulate more ice and more ice. So this storm in the background, as I mentioned, which was from Oklahoma a few years ago, it produced hailstones with diameters as large as 10 centimeters or 4 inches in other money. And so you could imagine that would do a huge amount of damage to your property, to your car, very dangerous to be out in, and unfortunately is very damaging towards animals and maybe livestock that might be out in the fields as well. So thunderstorms can also have very, very strong winds. That is because if you've got lots of rising hot air, you also have to have descending cold air. And the cold air, as it's ascending, can accelerate very, very rapidly. And when it hits the ground, it sort of pushes out. It's a bit like if you drop water on the ground, it'll flow out to the side. So the air does the same thing. And this can generate very, very strong winds underneath a thunderstorm. And then the other major hazard you can have are tornadoes. Tornadoes are most commonly formed at the base of severe thunderstorms. You need one more ingredient, one more major ingredient, which is rotation. You need to have rotation in your thunderstorm. So this can come from a number of different ways, primarily through something called wind shear. So what wind shear is essentially is if going up through the atmosphere, your wind is changing in speed or in height. So if you think about, say, if you've got a pencil in your hand and you move your hands in opposite direction, the pencil is going to spin. So similarly for a large thunderstorm, if your wind is coming in different directions at different heights and it's pushing and forcing your cloud, it can generate rotational energy. And if that rotational energy can be brought into a thunderstorm, it can begin to rotate. So a rotating thunderstorm is known as a supercell, and it's a focusing of that sort of rotational energy that gives us a tornado. So what do these supercells look like out in the wild? So this is one from Oklahoma a couple of years ago that I photographed. The first thing you can really notice about it is this really amazing structure. It almost kind of looks almost like a screw, and it sort of hints at its rotational properties. It's also sometimes called a stacked plate structure. You can also see how active this is. A very, very strong lightning bolt. There's hail falling at the back, and there's a tornado just starting to form there off the base of it as well. So there's a small sort of a time-lapse video here, very, very short, but you can get a sense of the same storm. You can get a sense of the motion of the storm. You've got rotation happening here. You've got these clouds kind of rolling forward. Let's play that again. And these things are really impressive to see rolling across the landscape towards you. It's like an enormous spaceship or something coming towards you. It really does make an impression. So can we get severe thunderstorms like that in Ireland? So we have some of the ingredients. We certainly have moisture, as you know. And we do have unstable air. However, we don't really have the same sort of heat energy, excuse me, that you have, say, in places like Central US or Central Europe. The main reason that the air is unstable is because the air above us is so cold. So relatively speaking, the air at the ground is warmer and it wants to rise. But we don't have that same driving capacity that you might get in places that are more commonly get severe storms. We do have wind shear here as well, so there can be some rotation. But again, our thunderstorms aren't really growing enough to really sort of make use of that. So essentially, we frequently get small thunderstorms here in Ireland, but we very rarely get very severe thunderstorms, or those that are rotating, which are, as I mentioned, called supercells. They do happen though. We do get some spectacular storms now and again. This was taken not too far from here at Mullockmore in Sligo. This was also last summer again in Sligo at the sort of the middle of June. We'd had a lovely May and start of June, and then sort of the break between the two, sort of the warm weather and the rain was marked by some really powerful thunderstorms. This is that same day, a thunderstorm approaching southern the south of Sligo. This is a little bit sped up, obviously, but you can see it's a very, very dynamic system. The cloud is rolling. You've got very, very disturbed air underneath the thundercloud. It's a large system stretching down here. And a huge amount of energy in these systems. And these storms did actually produce quite a lot of lightning, some damage in Roscommon as well. And obviously, as many of you will know, there was a very well-known event that happened just this past December in Leitrim Village. So on December 10th, Storm Fergus crossed over Ireland. Now, I should say, as you would have seen from my background, I don't work as a weather forecaster. I'm not a weather forecaster. So this is sort of a personal interpretation of what happened, rather than say an official Met Éireann report on it. But I've also consulted a good friend of mine, Paul Downs, who is an expert in severe weather, and he also gave me some assistance on this. So Storm Fergus, you can see in this satellite imagery, it's just approaching the west coast there of Ireland. That's the center of it there, and it's spiraling around, and it crossed over Ireland through the day. But if we go back to the 1 o'clock image, so just before this, we had reports of severe damage and a possible tornado in Leitrim Village, roughly around 12:40 or so. So there's Leitrim Village there. So I'm sure many of you have perhaps seen this clip already. This is a video that was recorded at that time. You can see these little flashes are not lightning, they're power flashes. That's from electricity poles been hit by the storm. And you can see some of the debris that's been lofted up here does appear to have sort of a rotational path to it, suggesting that it is tornado damage. So we have a line of cloud, as you can see, kind of at the front edge of Storm Fergus as it was coming in. And this area had a lot of unstable air. So as I mentioned, that was one of those real key ingredients for thunderstorm formation. Some analysis of this area after the event also indicated that there was potential for rotational energy. So that's sometimes referred to as helicity, but basically that capacity for getting these storms to start rotating. So we have radar imagery of a thunderstorm that passed over Leitrim Village at that time. So there were some reports of thunderstorms prior to that event. So here we have a thunderstorm formed over Galway, and it's moving northeastwards. So you can see with the radar imagery, these kind of darker purples and reds and then to grey mean more intense precipitation and potentially hail. And we can see it really intensifies where it hits Carrick and Shannon, and then passes right over Leitrim Village at around the time that the damage was reported. So just to kind of focus in that a little more, this is just as it intensified over Carrick and Shannon, and then it moved onwards. So one thing I should say about this radar imagery, this has been monitored using the Shannon radar. So Shannon radar, as a crow flies, is more than 150 kilometers away. So radar, its accuracy decreases substantially, particularly once you get more than 100 kilometers away. So it means, unfortunately, we don't have great sort of detailed imagery of what's happening at that space. However, there is a signature. If you say, for example, I'll show you this now. This is from a radar system in the US. So the US is great for these kind of systems. They have radar units dotted all through the country because they get this severe weather so often. And a signature that they look for is what's called a hook echo in the radar. And that's basically, this is sort of rainfall coming out of a cloud or precipitation, but you can see that there is a swirl or a hook in the echo, and that is evidence of rotation taking place in the cloud, and can be a precursor or a signal that tornado may be about to form or has formed. So I know it'd be very hard to see from where you are there, but there is a slight evidence of hook in this imagery here and also there as well, which may indicate again sort of a tornadic rotation system. So we can get severe events, but they're very rare. Excuse me. And how is our climate going to respond in the future? Will we see more severe weather events as we go forward? So looking at our climate, firstly taking, say, a global picture, Ireland has pretty much tracked on course with the global average. So we've seen about a 1.3 degree rise in temperature since the start of the Industrial Revolution. Now, I need to emphasize that is an average value. So there are parts of the world that have increased much warmer than that. So the Arctic, for example, has increased more than 4 degrees Celsius in the last 50 years. There are parts of the world that are very, very sensitive to temperature increase, particularly the Arctic. Places where it is already too warm to grow food, there's insufficient water, places where it's too warm to work. These are real concerns, and where there are a lot of sensitivities to increases in temperature. Now, I'm not going to go into great detail on climate. That's a whole talk on itself, and I'd be happy to do that another time as well, but just to kind of give an overview on that. Where is that temperature going? It really depends on the pathways that we take. So we could choose a number of different pathways in terms of how we choose to respond in terms of carbon emissions. If we decide to be as sustainable as we possibly can, bringing things down to a carbon neutral or a carbon negative, if even possible, we're looking at a temperature increase of about 1.5 degrees Celsius on average. If we were to take moderate action, what I mean by moderate action basically is that if all the promises we are making right now, if we fulfill them, we're looking at about a 2.8 degree increase in temperature. And again, that's on average. There's regions where that will be extremely pronounced in terms of temperature rise. If we only focus on establishing our own plans, say, for example, Europe works together to try and reduce carbon emissions, China does its own thing, America does its own thing, we're looking at upwards of 4.2 degrees Celsius on average. And then if we just continue sort of business as usual with the fossil fuel economy, upwards of 5.5 degrees Celsius. As I mentioned, that would equate to rises of over 10 degrees Celsius in certain parts of the world. So let's bring it back to Ireland. What does this mean for Ireland? So even not looking too far out into the future, say by the middle of the century or by 2060 or so. So depending on what progress we make, what sort of emissions progress we make, it's sort of a middle of the road progress. We're looking at an increase of between 1 and 1.2 degrees. And if we sort of continue business as usual, up to 1.6 degrees increase. That's on average, but we'll see a much more pronounced impact at the extreme ends of our climate. So what I mean by that is our summer, sort of the hottest temperatures we will get in the summer and the coldest temperatures we would get in the winter. Those are the ones that are going to be impacted the most. They're both going to increase. So depending on the choices we make, it could increase by up to 2.2 degrees during the summer and increasing by potentially up to 2.4 degrees in the winter. So what are the impacts of that? You know, maybe it doesn't sound so bad. So one is that we're going to see an increase in heat waves during the summer months. So this is potentially up to maybe somewhere where you might be getting 1 or 2 heat waves every 2 years. You might now be getting up to 8 or up to 15 within, say, a 10 or 20 year period. The increase in the winter temperatures means that we will see a substantial reduction in the number of frost and ice days that we get. Now, many of you may know that the frost and ice days are really important to our natural ecosystem. They can be the trigger for a lot of natural processes that take place. They can be important for killing pests, for agriculture, and also for our other natural ecosystems. And our ecosystems will not be able to respond fast enough to the changes that are happening here. So we're looking at, even in a moderate, even if we respond with sort of relatively good action, we're looking at a reduction in up to 72% in frost days. So that's a huge change by the middle of this century. And then, as I said, if you know, more than 80% if action is delayed or is slow. And how about, that's our temperature. How about our precipitation? So we're going to see a sort of a more extreme profile to our precipitation. So what I mean by that is we're going to have more dry days and more very wet days. So we're seeing a sort of an increase in, you know, up to between 28 and 47% in drought periods, in frequency of occurrence in droughts. And then conversely, we could see increases of up to 50% of very wet days. So that sort of that profile means that we're going to, as I mentioned, sort of more extreme profile in our rainfall. This is important for planning because if, say, for example, you're planning a project and you're relying on sort of metrics that say things like, well, this is a 1 in 10 year event, this is a 1 in 50 year event, those may no longer be valid because you're talking about a much higher frequency of very wet days where flooding events could become more frequent in your area. So just a summary on that point in terms of our future climate. So as I mentioned, we're pretty much warming at the global average, and that's expected to continue. We're going to see a substantial increase in our maximums in the summer, and that's going to lead to increased heat wave frequencies, and then an increase in our winter minimum temperatures, which is going to lead to that decrease in frost and ice days, as I've mentioned. And our rainfall is going to be more in extremes, so more droughts, more very wet days, and that is going to be impactful for those, as I said, who are involved in planning, involved in water management, agriculture, and lots of different sectors. More heat energy and also more moisture, because a warm atmosphere can hold more moisture, means there will be more energy available for extreme weather. So it means when extreme weather does occur, there'll be more energy there and more capacity there for them to be extreme and potentially more damaging. So that's been kind of a sort of a whirlwind tour of a range of different aspects of our weather and climate. Some very, very positive, lots of really good things to look forward to in terms of improving how we forecast the weather, how we understand our weather and climate, and how we can potentially track and understand severe events also and prepare better for them. And also some words of caution of what we look to when we see the future. So I'm happy to take any questions. It's been lovely to talk to you this evening. If anyone would like to get in touch with me, I have a website, bigskiesmedia.com, or you can get me on social media at Big Skies Media as well. But thank you very much. So yeah, your question there in terms of is the Gulf Stream and its potential slowdown being considered in our climate projections? It is. So as you say, I suppose there's some I don't know if any of you are aware, there's a movie that came out years ago called the day before tomorrow, the day after tomorrow, something like that, and it depicts the shutdown, and it's very dramatic and very cataclysmic, and I think it makes climatologists nervous to talk about it because like it's not going to be like that, but it is, as you say, there have been reports coming out that it's slowing down. And that is included in the climate models. Or climate models, depending on which model you're using, will also not just look at the atmosphere, but it'll also have the ocean system included in it. So it's like a paired system. And the general view on that is that it will lead to a cooling because we bring a lot of warm energy up from the Gulf of Mexico towards our, and that's why, as I'm sure you know, that's why our climate is milder than it would be, say, for example, say if we're in Moscow or parts of Canada, which don't have the influence of this. However, based on the current rate and the current understanding, is that the rate of global warming will outpace the cooling due to that effect. Now, that's based on current understanding of how that, as it's called, it's the overturning Atlantic meridional circulation. The pace of that, based on current observations, that's the consensus view that global warming will outpace the cooling because of that effect. However, as you quite rightly say, it's not a fully understood system. There are some major features which could impact that, primarily, which is kind of more my background, is the melting of the ice caps, because you're dumping a whole bunch of fresh water into these systems. And a lot of these systems are driven by differences in density and temperature. And by inserting a lot of fresh water into these systems, you can upset them, and that's what's causing the slowdown. So to answer your question, it is considered, it is included in models. The current view is that it's not going to outpace global warming, but it's certainly not a fully understood system.
Thank you.
Sure.
Francis? Fantastic talk. Made it so simple for and easy to understand weather and how it happens and so on. So just one question in relation to the tornado and Leitrim. You talked about the warm ground and the warm weather, or the warm at the bottom.
Yes.
So this happened on the 10th of December when you wouldn't typically think it would be very warm, particularly Leitrim. Everything around.
Yes.
So could you comment on that for us, please?
I can, of course. So your question being that how can we get these sort of strong developing thunderstorms in December when the weather's quite cold and you're not getting that driving heat energy? So I think in one of my slides, I could put, well, actually, I will go back, it'll take a while, but the most, the driver is the relative difference. So here in Ireland, we have lots of very cold air above us because we're not too far away from the thing called the polar front. So that's where cold air coming down from the north. And therefore, the air on the ground doesn't need to be particularly warm to be warmer than that air above. So it's the relative difference between the two. Now, as I mentioned, it does, for the most part, limit how strong these storms get. Even the storm that impacted Leitrim, it wasn't a particularly tall thunderstorm. And generally, you need these really tall, big thunderstorms to sort of access that really powerful sort of rotation energy. But the importance, and in fact, we actually get most of our, or a lot of our thunderstorms anyway, during the winter months, because of the fact the air is so cold above us. They're not strong, they're not major thunderstorms. You might only get a few flashes out of them, but it's just provided you've got a difference, then there's the capacity for that kind of process to take place.
Yeah, is there something about, let's say, Leitrim or Sligo, are we more likely to be getting these type of events? Or like I know Ireland is much smaller than America. Is this the sort of tornado valley of looking at, or no, could have happened down the south just as easily or further north?
So are we prone to these kind of severe storms in the northwest? It's a good question. To be honest, I don't think there's evidence to say that at this point. One of the things that we do have, obviously, is we've a lot of moisture coming off the sea, which is an important ingredient. You also can have, which I'd sort of detail that I didn't go into in the presentation, in addition to all those features, you usually need something to kind of give the storms a little bit of a kick to get going. That can often be, for example, you may have heard when a weather system is approaching, it's called a weather front. And at a weather front, there'll often be sort of one, say, form of air riding over another form. That can act like a little bit of a ramp to kick off these thunderstorms to get going. Or you can also have changes in wind direction at the surface can also sort of be another feature. So it's possible where we're based, because we're getting so many of these systems coming across, we're kind of like the first place that samples it for the rest of the country or for the rest of Europe, that we have more conditions conducive to their forming. But I don't think there's been, as far as I'm aware, there hasn't been sort of a climatology study to say if this region is particularly prone. But it would be interesting going into the future when we get more heat energy to see if it is a hotspot. So generally so good question there. So would I blame CO2 totally for global warming? CO2, you'll often hear CO2 used, and also another term, which is CO2 equivalent. So what that means is it's saying, like, because it's not just CO2, essentially, is where I'm going. So there are other gases. Methane is another important one. But it will be expressed in terms of, say, methane is about 4 times more powerful as a greenhouse gas than CO2. So, correct, yes. So I suppose essentially it's CO2 or CO2 equivalent is often used to talk about emissions, but it's not the only driving factor. And also, emissions themselves are not the only driving factor. It's there are a number of processes in the atmosphere that are called climate feedbacks. So emissions can be sort of changing the chemistry of our atmosphere by adding, more carbon or more methane or other gases into the atmosphere can be a trigger to start some of these processes. So one that's very, very important and prominent is the loss of snow and ice. So if you think about imagine a hot day and you're wearing a white t-shirt and then you change into a black t-shirt, you're going to feel a lot more heat when you're wearing the black t-shirt. So our snow and ice does the same thing for the planet. It reflects a lot of the heat energy from the sun. But when we get into a process where we warm the earth slightly, we lose some of that snow and ice. And therefore we have less sort of reflectance. So there's more energy being absorbed. The planet gets warmer and melts more snow and ice. And then you get into this kind of vicious cycle where it gets warmer, more ice goes, more warming takes place. So that's one example of a climate feedback. It's not an emission. It's been triggered by increases in emissions, but it's its own system. And it's basically where we're unbalancing a natural system and we put it out of equilibrium. And that sort of is a driver in itself of climate change as well. Oh, it's a very, very good question. So if we have our computers based in Iceland, surely that is not a great place to put them, considering how many sort of natural hazards they have there, as you say, volcanoes and earthquakes. So this is very true. It's not the entire island, is the first thing I would say. So there are regions in the island based on known faults where the activity occurs. So where earthquakes are most pronounced, where volcanoes are most frequently occurring. A geological survey was done when that bunker was built initially. So as I mentioned, that bunker was built during the Cold War to be both a nuclear shelter and protection from natural disasters. So they selected a location that was geologically sort of safe and quiet. And then they, as I said, they enhanced it then by building a really secure bunker with multiple different sources of power coming into it. So not only is it relying on electricity generated from outside, it has its own power generators internally. So it's a very good question based on a lot of sort of research and, as I said, not just construction, but also through looking at the geology of the area. They were confident that it was the safest place in the island to build. But it is a very good question. Yeah.
Oh, okay. Sorry, yeah.
Hi.
I just want to ask a question on I suppose, the radar infrastructure in Ireland and what it looks like at the moment. And we mentioned Limerick radar.
Yes.
I follow some of the forecasting websites in Metbox and Meteorologist.
Yes.
Is there anywhere else on what the plans?
Yeah, it's a great question. So in terms of our sort of our radar network in Ireland at the moment, what are its plans? So there's a project ongoing at the moment. So as you say, we have in the Republic of Ireland, we have 2 radar stations, one at Dublin Airport and one at Shannon. But we are now expanding or in the process of starting to expand that. So potentially increasing by another potentially maybe 5 radar units. So it's a huge project. Again, that number could vary as well in terms of how many it will be. It's tricky to get planning permission as well for some of these units. But it's been driven by some of the things I mentioned during my talk. Really, once you get beyond 100 kilometers, the radar units, their effectiveness really drops off. And particularly on the West Coast, when really we're the first place in Europe that's sampling a lot of this weather. So there is a big project to expand this. It's sort of midway through the planning phase, I would say. So it's still a few years before you're going to see these radar units built. But it's not something that's sort of like an ambition. It's definitely going to happen. It's well underway. Contracts are being signed, all that kind of stuff. So it's coming, but it's still a few years away. What I would say is the new satellites that are going up, because they have such good resolution now and because they're being updated so frequently, I'm very interested to see things like rainfall products from them that could help fill some of those gaps. The question was in terms of how hazards might affect power lines going forward and things like ice formation or wind, and if that might change in the future. certainly our wind is expected, sorry, excuse me. On average, which might sound surprising, the models are showing a slight decrease in average wind speed in Ireland as we go forward with a warming climate. Now, that is on average. That doesn't mean that, as I've mentioned, it's likely that when we do get severe events, storms, that they will be stronger because there's more energy for them. So what you may see is that there is maybe a reduction in risk on average through the year, but then you're having higher impact events when they do occur. Now, that's a general sort of a view, but say, I know, for example, those interested in energy production through wind power, very interested in the fact that there is actually going to be a slight decrease, probably in overall wind speed as we go forward. Now, I'm talking about in the order, the exact figure, I'm not certain, I think it's about 7% decrease, but it's not insignificant. So that is, so that's probably in terms of wind, I would say you're looking at a higher risk during isolated extreme events is probably what you're looking at, the higher impact. In terms of icing, as I mentioned, we're seeing a big decrease in the number of ice days going forward because of the fact that our minimum winter temperatures are increasing with warming. So I would imagine icing is going to be a reduced risk going forward.
Flooding?
Yeah. So is flooding going to be a risk? Absolutely. With the profile that our rainfall is taking, pushing it to more sort of an extreme profile, more drier periods, more very wet days. So you're getting more of your rain in a shorter space of time. And again, that really comes into future planning. If you're planning for flood defenses or drainage systems, the sort of metrics that you might have used before to say like, okay, this system can handle a 1 in 20-year event, that may no longer be valid by the middle of this century.
What sort of, can you put a figure out in percentage
there? So in terms of volume, off the top of my head, I can't give you that percentage. I know in terms of the number of very wet days, the profile varies through the country, but it's over 50% in some places. You'll see an increase, assuming that we carry on our current sort of emissions and climate change sort of direction and pathway. There is more targeted information for specific questions like that. So it's a good chance to mention it. There's a project called Translate. It's an Irish project to gather climate information and climate projections into one location, because there's a lot of information out there. So if you want to go to one place to gather that information, so it's called Translate. There are a number of different bodies who contribute into that, including Meteorologist. So if you would like to sort of go to one place, it's kind of the first step towards a decision-making portfolio, I guess, to allow decision makers to have a place they can go to get the information they need for their various use cases. So Translate is the first step of that. So that's maybe you could probably get a specific answer to your question.
Sorry, the 50%, is that over a 20-year or 50-year time then?
Yeah, so that is over a 20-year period. And again, that's for that metric refers to the period between 2040 and 2060. And that is obviously on a sort of a business as usual if there's no one.
Oh yeah, how about lightning?
It's a good question, to be honest. So would lightning be another risk factor or an increasing risk factor? Based on the potential to have more heat energy and more convection, so that's basically that word of where you're getting uplift and you're getting thunderstorms forming. It's possible. I haven't seen a specific value for lightning increase, to be honest. So I won't say it because I don't actually have that information. But the logic would be that it's likely you will have more thunderstorms, so it's possible.
Okay, I'll take the last one. So I've got a number of questions online. I'll take two. Okay,
mine was a double, so it was. They were about satellites, and just firstly will it be available, that imagery, to let's say any member of the public be able to see it themselves? And I'm just curious how they're all over the equator rather than centered more over Europe. And is that just to do with to get them into the geostationary orbit that equator?
Exactly. So regarding the satellites, will the imagery be available first and foremost? It will be through in a way. So the data will come in the priority is to get it in as quickly as possible to forecast offices. So that's the first priority. It's funneled in as quickly as possible. We'll be pulling it down as quickly as we can to get it to the forecasters. And then through our channels, the satellite data will be available, whether that's through imagery on, and I'm just speaking, say, I'm saying there's obviously any sort of forecast office in Europe, through imagery available on the website and through the app. There are also then the agency that runs Europe's weather satellites is known as EUMETSAT. They have online repositories of all this data, and you can sign up to access those repositories and download them yourself as well. So the data will be available. Just in terms of how quickly you can get it, that's where the difference is. So it'll be sort of the weather forecasters. That's who will get the priority for getting the data as quickly as possible, and then a little bit further down, the data will be more generally available. Your other question then in regards to why are the satellites based over the equator? It's exactly for the reason that you said. It's so that in order to keep them maintained in what you call a geostationary orbit. So geostationary, as it kind of suggests, means it's stationary over one part of the planet all the time. So the Earth is rotating, but the satellites are rotating at the same pace. So they're constantly looking at Europe. And that's why they're located on the equator and located the distance away that they are, 36,000 kilometers, to maintain that orbit. So how do we get seawater temperatures these days? So from talking to my colleagues in the marine division in Met-Éireann, I know that they still have an interest in obtaining ship obtained measurements. We have, as you mentioned, primarily we're obtaining the data from buoys. We have a number, as I'm sure you're aware of, we have a number of anchored or moored buoys around the country, but then we also have a series, when I say we, I mean the scientific community, there are a series of drifting buoys in the ocean as well. So they're not moored, they're free floating, but their position is known by GPS, and they're transmitting data regularly, giving values back on sea temperature, things like that. But profiles of temperature from ships is still sought and is still an important value. Now, there's a range of quality control processes that take place because obviously, depending on the age of the equipment or at the location of the ship, some data is more reliable than others, but it's still considered a useful source of information.
I'm going to take some of the online. Will the UWC models replace the current Met-Éireann forecasting models, Harmony, or will they be used alongside one another?
Sure. So will the current Met-Éireann models be replaced by the new UWC models? So through this Iceland and Denmark and the Netherlands. So at the moment, they are being used in tandem. So essentially, the question there, the person mentioned Harmony. So that's the name of the weather model that we currently use in Met-Éireann for short range forecasting for Ireland. So our forecasters, that's the primary model that our forecasters are using, but they're also now looking at the new model from this UWC, and they're comparing how the two compare. Once UWC goes active, that will be the primary model. However, the architecture that underlies that new model is Harmony. So essentially, it's like a newer, updated version of that same model. It's been applied to a bigger area, and it's been updated. It's running at a higher resolution and more frequently, but it's the same architecture that the original sort of Met-Éireann model is built on.
Will the forecast collaboration still make use of ECMWF data, or will this be a standalone forecasting system?
It will. So the main way it will use the data is in terms of establishing what are called the initial conditions. So what I mean by initial conditions are, when I mentioned at the start the different ingredients you need for generating a forecast, I emphasized how important it was to have good observations, because you need to know what your weather and your atmosphere is doing before you can start trying to forecast it. Because if you don't know with a high level of accuracy what the weather is doing right now, your forecast will deteriorate with time. So what the ECMWF, so that's the European model, will be used for is essentially filling in gaps where we don't have observations. So we'll be using we're using model data. It kind of sounds like a bit counterintuitive, but it's essentially we'll be using what we consider very, very accurate weather model data to act as observations where we don't have real world observations. So that'll be the main role that the European model will be playing going forward.
You mentioned a few countries that are involved in the partnership: Ireland, Netherlands, Denmark, and Iceland. What are the other European countries doing, and do you know why they didn't participate?
So, well, so it's a good question, and I'm glad to say that this can be considered as the first phase. So I'm referring to it as UWC, but technically this is UWC West, so United Weather Centre West. And this is the first phase where, as I mentioned, the 4 countries are taking place in it. There will be a total of 11 countries in that collaboration once it's fully operational. So we will operate ourselves for a few years, and then the Nordic countries and also Spain and some countries in the Baltic Sea will be joining the collaboration. So it'll be a consortium at this stage of 11 countries. So it will be much broader once it's up and running. There are other collaborations, and then other agencies are just, if you think about the UK or France or Germany, some of these agencies have huge weather services, and for them, they're progressing with their own. Maybe they don't have the same need to work together, but it is a very collaborative landscape either way. Even if the models are been run differently, weather doesn't know any political boundaries, obviously. So there's a lot of collaboration in sharing data, in sharing observations, and sharing model output. So this is a starting point. There could very well be more collaboration going forward.
Can you discuss clouds in Ireland and the scale of the impact on cloud cover of climate change? And also, why is Ireland so cloudy, particularly in the winter, and is it cloudier in the evenings here?
What was the last bit there, sir?
Why is Ireland so cloudy? The questions relate to impacts on solar energy production.
So in terms of why it's so cloudy, the main reason is that we have very moist air flowing off the Atlantic. So where we are in the world, the primary flow of air is coming from the west. So there's sort of bands of air. If you were to look at the globe and you could see where the air was flowing, there are very sort of general bands across the earth. Some are flowing west, some are flowing east. And where we are, the air flows primarily from the west. It's pulling very moist air over the country nearly all the time. We have lots of coastal hills and mountains, which forces that air upwards, which causes the air to condense and to form clouds. So we're in a very moist environment, and we're also a relatively cool place. So it doesn't take much for cloud droplets to form, because in cooler air, clouds, water vapor will form droplets much quicker than it will in warmer air. So it's a combination of very moist air, very cool air. In terms of climate, it is one of those really, it's one of the big questions in terms of how cloud behavior will change going forward. So to be honest, I won't give you a sort of an answer on how the cloud is going to change, because I couldn't give you a sort of an accurate answer as far as I feel, because it's an active area of research. There's some, because of the fact that we'll have more moisture in the air, believe that there'll be more cloud around. But it's not a definitive, it's probably the biggest unknown in climate science at the moment.
Are there plans to provide improved wave forecasting model services for Ireland?
So there is, as of about 6 months ago, a new wave forecast. A new wave forecast provided on the Met Éireann website. And now this is kind of really an initial step as far as I'm concerned. Anyway, it provides wave height, wave period, and direction, and it also breaks down the waves into swell, which is kind of waves that are coming from storms and systems that are further out to sea, and they're kind of organized waves by the time they come to land, and then sea swell or sea waves, which are generated by sort of local winds. So that's currently available, and it's my hope that there's going to be a more advanced model made. I'm a surfer myself, so the more forecasts we can get in that aspect would be great. And it's my understanding that there will be, but there is an initial step there at the moment, and it's on the Met-Éireann website.
How do you class Met-Éireann's forecasting accuracy for specific locations for 24 hours or less ahead? I am thinking about detailed forecasting accuracy for the likes of the Ploughing Championship or other large multi-day outdoor events.
So in terms of what's available, Met-Éireann are the only people who would be running a high-resolution forecast model for Ireland. So what I mean by that is, say, for example, if you on your smartphone, you might often get a sort of an automatic weather update popping up. That's generally coming from what's called a global weather model. And what I mean by that is basically it's generating a forecast for the whole globe or very large regions of the globe. And its resolution is quite coarse. So it's when I mean resolution, it's almost like the way I would describe it, it's kind of a bit like looking at your television from 20 years ago. The picture isn't you can't really see the fine detail. Whereas Ireland is, Met-Éireann are running sort of the 4K model for Ireland. So it's just focused on Ireland. It's limited in time. It's only running for about 54 hours into the future. But the idea being that we're the only ones running this sort of the accurate short range forecast for Ireland. In terms of its performance, one of the areas that we're really focusing on going forward is an area called nowcasting, and that's really short range forecasting. That's where you're kind of combining observations of what the weather is doing right now with really short-term forecasts, sort of 3 to 6 hours into the future. That's something that I'm quite excited about, both from the new satellite products that are coming and maybe the radar network that's going to expand as well. We'll have a lot more information for improving those kind of really short-range forecasts. In terms of how accurate do I think they are, there is ongoing verification in Met-Éireann. So it's not like, we run it's not a sort of a hand wavy exercise. We actively compare what our forecast is with what our actual measurements were after the fact. It's an ongoing process. There's a section in our organization focused on that. So it is actively measured. I don't have the exact figures for, say, something like the Ploughing Championships, but we do monitor when it goes right and when it goes wrong, and when it goes wrong, questions are asked, and we look to see how can that be improved.
You mentioned the potential for more energy to create more intensive storms in the future. Are we currently seeing a notable increase in high density in events, or can it be said that stormy and calm years go in cycles?
It's a good question. In terms of stormy and calm years go in cycles, that's not something that I've seen, and there's no guarantee that because you've had a stormy year one year that you're going to get sort of like a year off the next year. More often than not, it can be driven by sort of larger scale cycles. So we have short-term and long-term cycles in the atmosphere. Some are diurnal, so that's daily. Some are seasonal, and some are over multi-years. So there are ones like, say, for example, El Nino and La Nina. They occur, it's relating to sort of ocean and air currents in the equatorial Pacific, but because it's happening on such a massive scale, it does impact the weather around the world, and that can lead to cycles in terms of how wet or how dry a year might be or how stormy it might be. Its impacts here are a little less pronounced. They're more sort of obvious in North America and in parts of Asia, but it can have impacts on cycles. So I would say your sort of cyclic behavior is driven more by things like that rather than sort of like a year on, year off basis. And yeah, the first part of that was, are we seeing?
You mentioned the potential for more energy to create more intensive storms in the future.
Yeah, so it's the kind of the consensus view is that when they do occur, there will potentially be more energy available. So in two forms, one is more heat energy and then more moisture in the atmosphere. And as I kind of mentioned when talking about thunderstorms, moisture is like the fuel for a storm because as water droplets form, as a change from water vapor into water droplets that condense, you release latent heat, and that's a real driver, not just of thunderstorms, it's also a driver of tropical storms. Like we don't get tropical storms here because we're not in the tropics, but so from that perspective, you're increasing the fuel available to potentially have more severe storms.
That's all the questions online, and maybe we've got this good man. Are we okay to wrap it up with this? Sorry.
Just a question slightly off the ball.
Sure, yeah, no problem.
Given the sheer scale of energy in some of the storms that we have, and
yes,
forecasting and looking at wave energy and implications for wind energy as well, is there any research being done on trying to capture some of that massive energy that's been generated?
Sure. Do you mean other than wave and wind? Or?
Other than wave.
Yeah. Wave and wind are the big ones because, well, you don't have to be as geographically precise to capture those, because if you think about a big storm that we get off, a big frontal storm coming through the winter that we get off the Atlantic, the wind field for that is hundreds of kilometers. So if you have your wind farm within that area, it's going to capture the energy. Or if you have your wave buoys or your wave generators in that area, they're going to capture it. Things like, say, for example, smaller scale, powerful, say, thunderstorms, their occurrence is much more sporadic and much more variable in terms of the exact location, and you would need to have some sort of mobile energy capture to capture that. Also, it was actually, believe it or not, there was an attempt, a company about 10 years ago, not in Ireland, but in the US, looking to see would it be possible to capture energy from lightning storms. And the reality is that you are dealing with such a sudden, sharp amount of energy. As mentioned, some of these lightning bolts can be 30,000 degrees Celsius. They're outputting huge voltages in split seconds. And the reality is that you're going to waste pretty much all the energy in heat and in noise, because you're just, that's essentially what thunder is. It's heating the air rapidly, and it actually uses up a lot of the energy of the bolt. So in terms of usable energy, wind and waves are highlighted because they're sort of a broad sweep, and you can sort of put infrastructure in place that will capture it, from most directions or in most locations. So that would be, it would be very difficult to be more specific than that. Thanks very much.
Okay. I think that's it for this evening. Many thanks for your participation. It's great to see a crowd. It's great for us to be down here in Leitrim, and I think we certainly have to thank this man.